Okay, so we talk about what a hash function is and what I want from a cryptographic hash function. Now, question is, how can I construct a hash function? Okay, so I will talk about three construction methods. First one is creating a hash function from a block cipher. Then I will talk about Merkle-Damgard construction, which most of the known hash functions use. Then I will talk briefly about sponge functions and show how they can be used as a hash function, and SHA-3 is a sponge function, by the way. So let's look at hash functions from block ciphers. It is possible to construct a hash function from a block cipher where we replace the compression function with the block cipher encryption algorithm. Here I'm talking about compression function because think about it as a hash function. It is a compression function because the input can be of any size, but we are actually reducing it, right? Compressing it. So I will use a block cipher to perform this operation. If we already deployed a block cipher, we might consider building a hash function from it because we can make security claims about the hash function using the analysis of the block cipher. For instance, if block cipher is resistant to differential cryptanalysis, the hash function you are creating from this block cipher will also be resistant to differential cryptanalysis. Moreover, we can save space and implementation effort by reusing some of the components of the block cipher. Think about the small hardware. If you put a block cipher and a hash function, it will take a lot of space, right? But if you only put a block cipher and use it for both hashing and encryption, you will save the space. This is the idea. However, hash functions constructed from block ciphers are generally slower than a hash function with a dedicated design. This is why we generally refer hash functions instead of using block ciphers. So let me briefly explain how it can be done. Then I will show some pictures which will make things a lot clearer. But the idea is as follows. A compression function has two inputs, chaining variable h and the message m. So when you're hashing the ith message block, you're using the previous chaining value and obtain the next chaining value, okay? So you have two inputs and one output. Think about the block cipher. Block cipher has also two inputs, the secret key and the plain text block, right? And it produces a single output ciphertext. So instead of using a plain text and the secret key, I can use message, which I'm going to take the hash of it, and instead of the secret key, for instance, I can use the chaining value because a hash function doesn't use a secret key, right? These two parameters are public. Then I will produce an output which will be the hash. So if we, do many combinations, here actually we say that if we try to compress this, if you try to form compression function like this, you have the plain text, encryption algorithm, secret key, ciphertext, and chaining values, and so on. Then we can replace each k, p, and c with one of the values hi minus 1, their XOR, and so on. So this gives us actually 64 different ways to create a hash function from a block cipher. So instead of looking all of these 64 possibilities, we will actually look only 3 of them. But out of these 64 possibilities, 12 of them are considered secure, but 3 of them are particularly important. Davies Mayer, Matthias Meyer-Roseas, Miyaguchi Prenel. So let's look at all of them, but instead of defining them with algorithms or anything, let's explain them with a picture. So you have the encryption algorithm, for instance, assume that it is AES 128. So I'm using a block cipher of 128 bits and a secret key 128 bits. So I want to hash something, okay? So I divide it into blocks. So each message block here is fed into this encryption algorithm. Also a chaining value, initially it is an IV, for instance, are fed to here. So I perform the encryption. So I use here message block as the secret key, and I encrypt this IV, for instance. But at the end, I take it and XOR it and produce the next chaining value. So this is important because if I don't do this, you can go back, right? Because encryption algorithm is a bijective operation. But once you perform this XOR operation, you cannot go from here to here because you don't know this value and so on. But since if I need to encrypt more blocks, I take this, put it here, take the next message block, keep doing this in this way. So at the end, I will produce the final H value, which will be the hash of it. So it doesn't matter the size of what your message is. The output will be 128 bits if you are using AES because the block size is 128. So next thing is that here I use the message as the secret key, HI values as the plain text. So if you switch the places of these, like this is called Matyas Meyer OCS construction. Okay. So same idea, just places are changed. Also, if you take this and also put as an XOR here, it is believed that it provides more security. And this is called Miyaguchi-Fresnel construction. So you turn a block cipher into a hash function, and these three are somewhat popular. And if you want to use it, you can use it. But the output most probably will be the size of your block size. So generally, our block ciphers use 128-bit block size. So your collision resistance will be 2 to the 64, which is actually within our reach. So for applications where you need collision resistance, using a block cipher might not be a good idea. Okay. So let's look at the Merkle-Damgard construction. This is an iterated construction. So many hash functions adopt an iterative design to accommodate a variable length input. Merkle-Damgard construction is the most famous one. Message M is divided into fixed length blocks. So M0, M1 to MT. This is your message. Then you apply a suitable padding, like we did it in block ciphers, putting a single one, then fill the rest with zeros. Message blocks are compressed one after the other to produce HI using a compression function F. HI is called a chaining variable and used in the compression of next message block MI plus 1. Compression function uses MI and HI minus 1 to produce HI. This is the summary. So H0 is fixed and specified as part of the hash function specifications. In other words, it is just IV. Sometimes a finalization operation is applied to overcome some attacks like length extension attacks and so on. So let's look at a picture and understand what we are trying to say there. So you have the message M. It could be something small like 10 bytes, maybe it is 10 gigabytes. You still apply a padding. So this is your whole message. Then you divide it into blocks, like what we did in block ciphers. But here, generally, the block size is larger, like 512 bits or similar. So you have a compression function F. It takes two input message block and IV, which is H0, your chaining value. So the input is actually large, but the output size is fixed. This is why we draw this picture like this, okay? So you produce H1. But if you have another message block, you put it here, you do the same, you do the same. So at the end, you produce the hash. Regardless of the size of this message, as you can see, the output is the size with this HI values, okay? So whenever you hear hash functions like MD5, SHA-1, SHA-2, they are actually this F function, okay? So whenever I say this is how MD5 works, I will put it here, okay? Because they're all Merkle-Damgard constructions. So you are actually defining a compression function by saying MD5, SHA-1, SHA-2, okay? So this picture should be clear. So because this is the main construction method, then we will talk about what MD5 is doing here, or SHA-1, how it works, or SHA-2, and so on. So many popular algorithms use Merkle-Damgard construction, and most of them are broken, like MD4, MD5, SHA-1 are broken. So SHA-2 is secure, but it is also Merkle-Damgard, so we were interested in new designs. So sponge functions are a good options to generate new family of hash functions. So a sponge function can be summarized like this in this picture. So the idea in a sponge construction is a little bit different. So in a sponge function, you have a huge internal state. Here it is represented like this. So R plus C bits, but it can be 1,000 or 3,000 bits. It is a huge state. Then what you do is as follows. You XOR your message blocks to some part of this big internal state. Then you perform a permutation function, which actually mixes this internal state. Again, using the ideas of confusion and diffusion like we did in block ciphers. Then you XOR the next message block to here. So this is called absorbing phase. So think about the real sponge. You tap the water and you are filling it water. So you are absorbing message in your sponge, okay? And at each step, you are mixing the internal state, so the information is fixed. And after the messages are done, you again perform the F function. Then Gradually, you provide output. Here, for instance, R of your bits are produced as 0, but this is, for instance, not enough for you to as the hash output. Maybe this is just 64 bits, but you need more. So you perform the F function again, mixed internal state again, then produce another 64 bits and so on. You do it until you feel how many bits you need. So this is squeezing phase. You squeeze the sponge, some water, goes out. This is the idea in a sponge factory. So here, F actually determines how you do this process. So SHA-3 algorithm will be here. Okay, SHA-3 is a sponge construction, so it will be using this idea.